This video is for my 7th grade math class and is over lesson 21, prime and composite numbers and prime factorization. So ladies and gentlemen, we're going to start by thinking about making rectangles using squares. You can almost imagine this like having boxes in a warehouse. So if you were working in a warehouse, you had 12 boxes and you wanted to arrange them into a nice grouping so they'd fit in the warehouse floor nicely. There are several different ways that you could arrange the boxes. One way you could arrange them would be to stick 3 of them going in one direction and then go out another direction 4. And so you would create a 3 by 4 rectangle. Now, mathematically speaking, this would be the exact same as if you did a 4 by 3. It's the same arrangement, it's just depending on which way you rotate it. So 3 by 4, 4 by 3, same thing. So how else could we arrange this? Well, instead of going 3 in one direction, we could just go 2. And then, of course, we'd have to go out 6 in the other direction. And so with our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 11, 12, excuse me, a 2 by 6 would create another rectangle using our 12 squares or our 12 boxes. Or you could alternatively just go 1 box across and maybe shove all the boxes right up next to the wall in one big line. So I got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so I could make a 1 by 12 grouping. So there are 3 different rectangles that I could make using 12 boxes. Now let's say we do some good business and we are able to send out some of our merchandise, but we haven't gotten any new stuff in yet, and so we've only got 7 boxes left now. So if I try to arrange that nicely, and by nicely I mean making rectangles, using my 7 boxes, my 7 squares, well, I can no longer go 3 across, because then if I go 3 across, I'd have 2 groups of 3 with 1 left over. I can't go 2 across because I could get 2 groups of 3, or excuse me, 3 groups of 2, but then again I'd have 1 left over. I can't go 4 across because I don't even have 2 full groups of 4. So there's really only one option that we're left with, and that one option is just to shove them nicely against the wall in a 1 by 7 arrangement. It really is our only option. And so, ladies and gentlemen, what we've discovered here is using diagrams, the difference between prime and composite numbers. So this number here, 7, is prime. And when we represent it symbolic or with an example like this, prime numbers are numbers where we can only make 1 rectangle. There's only 1 arrangement. Now up here, with 12, I was able to make not 1, but 3 different rectangles. So there are multiple ways that we can put these boxes together to make a rectangle. And so we call this a composite number. So composite numbers can make excuse me, can make more than 1 rectangle. So when you think about composite, the word composite has to do with putting things together. For example, when we get our photos back, our school photos back, there's an option to purchase a composite photo, which is the entire class arranged together in one photo. So you got everybody's picture all together in one composite photo. Well, ladies and gentlemen, this leads me now down to what if we have good fortune. We've been able to send out more boxes, but getting a little nervous. We haven't gotten any new inventory in yet. And so we're down to just our last box. So hopefully we get more in before this one ships out. Now the thing about having just one box, I can't really make a rectangle with this. Now a square is a rectangle, that's true. But it just is a rectangle. I'm not making a rectangle with it, it just is one. So, one, you can't make any rectangles with just one square, with just one box. Again, yes, it is a rectangle itself, but I'm not making a rectangle, and that's the key idea here. So because of this, I can't make a single rectangle, and obviously I can't make multiple rectangles. Well, if you can't make a single rectangle out of it, one rectangle out of it, it's not prime. And if you can't make multiple rectangles out of it, it's not composite. So what we've discovered here is that one, the number one, is neither prime nor composite. And ladies and gentlemen, that is going to jump up and cause some trouble here and there. Not very often, but here and there. Particularly if you're ever dealing with prime and composite numbers, you need to be aware that one is neither. One of the biggest places that students trip up on this is dealing with probabilities. For example, if we're looking at rolling a die, and I were to ask you what is the probability of a prime number coming up, well, we're going to count the number of prime numbers that would exist on the die. And so 2 would be prime, 3 would be prime, and 5 would be prime. And that's only 3 options out of the 6 total. So then our probability of a prime number would be 3/6. A lot of students, though, forget that 1 is not prime and want to add that as a 4th option, but it's not. Okay, so just be conscious of that, be aware of that. 1 is neither prime nor composite. So when it comes to our counting numbers, with regards to this, they actually fall into 3 categories. They're either composite, prime, or 1. Prime, composite, or 1. So let's go ahead and flip the page here. And while we have looked graphically at what does it mean to be a prime number and composite number, now we're going to define these. So a prime number is actually defined as a number with exactly 2 factors. Exactly 2. No more, no less. So 7 from the front, if I flip back to the front here real quick, 7 is a prime number because its factors would be the 1 and the 7 that make up its box. A composite number then is a number with more than 2 factors. And so again, if we flip to the front real quick here to look at it, so looking at 12, these are the 3 different boxes that I can make using 12 squares. So 1 and 12 are factors of 12, 2 and 6 are factors, 3 and 4 are factors. So 12 actually has a total of 6 factors. Well, that's more than 2, hence it's composite. And then finally, as we discovered on the front, 1 is neither prime nor composite. So ladies and gentlemen, We are now going to list all of the primes up to 100. And this list could be helpful as you work on your homework. So I'm going to teach you a few things to do with identifying primes later on. But to start with, we're just going to get the list here. So I'm going to challenge you a little bit. I want you to pause the video, and we're going to take these in groups of 10. So I want you to pause the video for a second and think, what primes are there from 1 to 10? So go ahead and pause. All right, let's see how you did. 2, 3, 5, and 7. All right, now let's go 11 through 20. What primes are there 11 through 20? Go and pause. All right, 11 through 20. We have 11, 13, 17, and 19. All right, go ahead and pause for the 20s. In the 20s, we have 23 and 29. So just 2 of them in the 20s. So hopefully you're catching some of these. All right, now pause for the 30s. In the 30s, we also have just 2 primes. So 31 and 37. Pause for the 40s. All right, 40s. We have 41, 43, and 47. Now, experience has taught me that a lot of students want to say that 49 is a prime. For some reason, we seem to forget about 7 times 7 is 49. So make sure we don't make that mistake. All right, moving on. 50s, pause. In the 50s, we have 53 and 59. Pause for the 60s. All right, in the 60s, I have just 2 primes, 61 and then 67. And I ran out of space here, so I'm just going to go below. All right, pause for the 70s. Okay, in the 70s, we actually have 3 primes. So one of the things that you're going to notice is the primes, as we get higher, do start to space out more. So there aren't going to be as many of them as often. However, every once in a while, we do get a clump that are a little closer together. So pause for the 80s then. All right, for the 80s, we have 83 and 89. And then finally, give the 90s a shot. All right, for the 90s, there's just 1, 97. A lot of people want to say 91 is prime, but it's not. That's actually 7 times 13, not a multiplication problem that you've probably done too often. Now, using this list, we're going to see how to find primes. Now, I don't expect you to have all of these memorized. You really should have your primes more or less, have a feel for them, probably at least up into the 20s, 30s, 40s, somewhere in there. As I start getting higher, I can understand if you don't have those quite down perfectly. So we're going to take a look at how to find primes using the ones that we should be most familiar with. So these smaller ones, especially up to 19. So to find all primes between 2 numbers, 1, you're going to write the list of all the numbers between those 2. So for example, down here, we're going to find all the primes between 80 and 100. So I've already done this for you. You would then do this on the homework for yourself, where you would start with 80 and write out all the numbers up to 100. So number 2, if 1 is in the list, cross it off, because we know that 1 is neither prime nor composite. Cross it off, it's not a prime. Number 3, we're going to do some thinking. So remember, red is thinking. You're going to find the square root of the larger number. Using your calculator will help you with this. So round off to the nearest number, whole number if necessary. So here we have 100 is the biggest number. So if we consider what is the square root of 100, that's where we get to stop. So square root of 100 is 10. So it means I get to stop at 10. So number 3, starting with the smallest prime, cross off the multiples of that prime. So our smallest prime, if we look at our list here, smallest prime is 2. And maybe you actually noticed, but 2 is special in the prime numbers because if you look at every other prime number, they're all odd. 2 is the only even prime number because all other even numbers are going to have 1 and themselves as a factor, but then they'll also have 2. So all other even numbers are composite. 2 is the only even prime. So down here, I'm going to cross off everything that is divisible by 2. So in other words, all the even numbers. So none of these even numbers are going to be prime. Let's just cross them off the list here. So we're going to continue crossing off multiples of other primes in order until we reach that square root. So that square root was 10. So until we get up to 10, then we're going to keep going. So my next prime is 3. So the best way to do this is to look at the list, and you can also include the stuff that's crossed off, and just find something that you know, real easy, you know 3 goes into. And I think the most obvious thing here is 90. We know that 3 times 30 is 90. So start with 90. And so what I'm going to do now is, since we're looking for things that are divisible by 3, I'm going to count by 3s and cross things off. So going up from 90, 1, 2, 3, cross off 93. 1, 2, 3, 96 is already crossed off. 1, 2, 3, cross off 99. Work our way down now. So 1, 2, 3 down, 87 is out. 1, 2, 3, 84 is already gone. And 1, 2, 3, 81 is gone now. Keep moving to your next prime. My next prime after 3 is 5. 5s are easy. We know that 5s are anything that ends with a 0 or a 5. Well, everything that ends with 0 is even, so those are already crossed off. So now I just need to make sure everything that ends with a 5, so 85 and 95, are also crossed off. So there's all my multiples of 5. And then finally, 7. And you'll see that 11 goes over this 10 we get to stop at. So 7 is my last one. So 7, I'm thinking, okay, 7, maybe there's nothing that obviously comes to mind here. So maybe I just think down to 7 times 10 is 70. And let's just start counting up by 7s from there. So 70 plus 7 more would be 77. Well, okay, that's still not on the list. Then 7 more than 77 would be 84. Okay, so that's the first one. And now that I found one on here, I can just start counting by 7s. So that's off the list already. 1, 2, 3, 4, 5, 6, 7 means 91's off the list. 1, 2, 3, 4, 5, 6, 7, and 98 is off the list already. And since the next prime would take me over my 10, my square root that I get to stop at, we're done. So what are my primes? Well, whatever's left over. 83, 89, and 97, which exactly matches what's in our list. Now, ladies and gentlemen, it is important that you know how to do this because what happens if the book asks you for the primes between two numbers that go beyond 100? Okay, so this list will be helpful, but it's not always going to save you. So you got to be able to make sure you know how to do this. All right, so let's take it through here now with another example, 40 to 50. So the first step, remember, is to write out all the numbers from 40 to 50. So I've already got them there for you. On the homework, though, you would write them out. We'd cross off any 1s. Don't have any, don't need those. Then we find the square root of the largest number, so square root of 50. If I take the square root of 50 on my calculator, I'm going to discover that that comes out at about 7. So it's 7 point something, 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 something. We just need the 7. So we're going to stop at 7. So I got to go up to 7. So we start with the smallest prime, 2. So get rid of all the even numbers, basically. So 2 goes into 40, 2 goes into 42, 2 goes into 44, 2 goes into 46, 2 goes into 48, 2 goes into 50. All right, now I'm moving on to 3. 3 is my next prime. And because of the clock, if we think about the clock, I know that 3/4 of an hour is 45 minutes. So that really stands out to me. 3/4 of an hour is 45. I'm going to have that be my starting place. So I start at 45, count up 3. 1, 2, 3. All right, already gone. 1, 2, and then we're out. All right, go down 3. 1, 2, 3. 42 is already crossed off, and 1, 2. Well, 3 were already out. So, okay, that was quick. After 3, the next biggest prime is 5. Okay, so 40, 45, 50. All right, already taken care of. Nice, 5's done. And then 7. Well, I know 7 times 6 is 42. And 7 times 7 is 49. Okay, cross off the 49. And that's all that would be there. And we're done. So 41, 43, and 47 are my primes. All right, if we flip the page now, we got a lot of reading here to refer back to if you need to. And then we'll do some examples on the back here. But to start, to factorize a number means to write it as a whole number, as whole number factors multiplied together. So in other words, if you want to factorize a number, just write it as a multiplication problem. So at the beginning of the lesson, we factorized 12. So 12 could be factorized as 1 times 12, because 1 times 12 is 12. 12 could also be factorized as 2 times 6, because 2 times 6 is 12. 12 could also be factorized as 3 times 4, because 3 times 4 is 12. So these are all factorizations of 12. 7, on the other hand, equals 1 times 7. And that is the only arrangement we can make. That is the only factorization of 7. That's why it's prime. So to prime factorize a number means to factorize it, but using only prime numbers. So this would not be prime factorized because 1 is not a prime and 12 is not a prime. This would not be prime factorized because 6 is not prime. The 2 is good, but not the 6. This would not be prime factorized because of the 4. 3 is okay, but 4 would not be. Down here, this would not be prime factorized because we're not allowed to use 1s because they're not prime numbers, but the 7 would be good. So let's see what to do to break this down completely. So, since we're only using primes, therefore our prime factorizations may not use 1 or any composite numbers. 1 just gets left out, but composite numbers will need to be further factorized until only primes remain. So we're going to have to keep factorizing until we get primes. Once the number has been factorized to only primes, we write the resulting primes in order. Let's underline that a couple times. That is important. In order in the multiplication problem. So if we take a look at a few examples of breaking 12 apart, the factorization of 12, 1 times 12, is not very helpful. 1 can't be used because it's neither prime nor composite. 12, though, would need to be factorized more, but then that brings us right back to where we started, needing to prime factorize 12. So really not helpful. In the case of 12 equals 2 times 6, we could keep the 2, that's prime, but we would need to further factorize 6. So we'd need to break 6 apart into primes. So 6 equals 2 times 3. So if I replace this 6 with a 2 times 3, then we get 2 times 2 times 3. So it's a multiplication problem using only primes. That's exactly what we're looking for. So that would be the prime factorization of 12 right there. We could have also used 3 times 4, so we'd keep the 3, but we would need to further factorize 4, so 4 could break apart into 2 times 2. So if we replace the 4 with 2 times 2, then we get 3 times 2 times 2. But remember that we need to put them in order. So we'd put the 2's first, 2 times 2, and then times 3. So what we see here is no matter the route we take, the prime factorization of 12 is always the same. It is always 2 times 2 times 3. The prime factorization of 7. Primes like 7 only have one factorization, 1 times 7. Since 1 is not prime and cannot be used in prime factorization, the prime factorization of primes is just themselves. Thus, 7's prime factorization is 7 equals 7. So anytime you get a prime number and you want to write its prime factorization, all you're going to do in your homework is write the prime number equals itself. So primes are real easy. We have two methods to help us find prime factorization. So this is really how we're going to show our work here. So what I'd like you to do to draw a little bit more emphasis to this is to grab a color. It's up to you what color you want to use. I'm going to use my blue here. And I'm going to put a box around this. And then I'm going to choose another color. I'm going to grab my green here. These are really our two methods that we use for showing our work. So first up is the factor tree. So we're going to write the number. Then below it, we're going to factorize the number by branching out, making an upside down tree diagram. We'll continue to branch out or factorize the composite numbers until only primes remain. Then we're going to write the primes in order as prime factorization. So, underline in order. I want to emphasize that again. So we're going to practice this right now on the back. So we're going to prime factorize, prime factorize 72 using both of the methods. So we learned the factor tree, so we're going to go over that right now. What does that mean? We got all the words there, but what does it mean? What does it look like? Okay. So what I'd like to see you do on your homework is branch 72 out. So I want you to take a full space here on your paper. So we keep all of our numbers nice and neat between the lines, a full space. And I'm going to branch this out. So it branches out going down. So it's almost more like roots of a tree. So what are the roots of 72? Where does it come from? So factor tree is nice because all I got to do is find factors that make 72. So what times what is 72? Probably the most common answer is 8 times 9. And so what we have to do is think through that list of primes that we had earlier. So if we think through our list of primes, is 8 prime? Is 9 prime? And the answer to both of those is no. So what I'm going to do then is I'm going to branch 8 out. Now remember, this is factorization, so we got to think multiplication here. So what times what is 8? What times what is 8? Now hopefully you just said to yourself 2 times 4. So now we're down to 2 and 4, and we got to ask ourselves, is either 2 or 4 prime? Oh, well 2 is. So what I want you to do is I want you to put a box around this. This isn't my answer, so I'm not going to circle it, but it's a prime, so that part of the tree is done. Put a box around it. Now 4 is not prime, so we're going to branch it out yet again. So again, what times what is 4? What times what is 4? Well, hopefully you just said 2 times 2. Well, of course, 2 times 2, those are both prime. So that part of my tree is done, but notice that we're still not done with that 9. So we got to come back up to the 9 now. I'm going to branch the 9 out. So what times what is 9? And hopefully you just said 3 times 3. Well, if you need to look at your list again, look at your list, is 3 prime. Oh, yeah, it is. So both of these now are done. So if we look for our squares are going to give us the prime factorization. So my prime factorization, I'm going to come up here. This is equal to 72. And I'm going to put these in order now. So I'm going to start with my smallest prime. My smallest prime is 2. And I have 3 of them. So I'm going to write my 3 2's out there. And then my next biggest prime is a 3. And we have 2 3's. That, ladies and gentlemen, is the prime factorization of 72. Now, if you want, though, Instead of writing the repeated multiplication, we could use an exponent to write this shorter. So instead of writing 2 times 2 times 2, we could write 2, but then there are 3 of them, so to the third power. Get that out of my shadow there. And then times the 3's, but there are 2 of those 3's. So this is 2 to the third power times 3 to the second power, or 2 cubed times 3 squared. That is the factor tree. So let's flip back over to look at the other method now. The other method is division by primes. And I want you to underline by primes there. That is the key to this method. It must be prime numbers you use. So number 1, we're going to write the number, and then we make an upside down division box, and we'll see why that works so nicely in a moment. Then we're going to divide by a prime number. It must be a prime number. The quotient will go below. Since it's an upside down division box, the quotient will go below. Number 4, we're going to continue to divide by primes until the quotient is also a prime. So what's going to happen is we're going to have only primes on the outside of our boxes. Finally, we're going to write the primes in order as the prime factorization. Again, underline in order. So let's see what this looks like. Lots of words there, but what does it actually look like? How do we actually do it? So I'm going to start with my 72 and make an upside down division box. So now I'm going to ask myself, what prime goes into this? What prime goes into this? Probably the most obvious thing is that it's an even number. So ladies and gentlemen, if you're ever feeling a little stumped, 1, go back to your list of primes and find something that goes into that number. But if it's an even number, real simple guys, divide it by 2. So if I divide this by 2, okay, we can actually do a little bit of short division here if you're familiar with short division. So we know 2 goes into 7 3 times. 2 times 3 is 6, which if I subtract that from the 7, would have 1 left over. So we stick this 1 over next to the 2, and we pretend like it's a 12 now. So now 2 goes into 12 6 times. So we have 36 left over. Well, is 36 a prime number? No. So then what we do is we make another upside down division box. We're going to just keep connecting them. So division by primes, what prime then goes into 36? Well, guys, it's still even. Let's divide it by 2 again. So 2 goes into 3 once. 2 times 1 would be 2. Subtract from the 3 would give us 1 left over. 2 goes into 16 8 times. Now we've got 18. Is 18 prime? No, of course not. At this point, maybe you notice, okay, hey, I know that 9 goes into 18. 9 goes into 18, so can we use 9? Well, is 9 a prime? Ladies and gentlemen, that is going to be one of the biggest mistakes here using this method, is not dividing by primes. So when we use this method, if it's not in this list, you can't divide by it. So I can't divide by 9, but wait, hang a second. I could divide this by 3. I know that 3 times 6 is 18. Speaking of 3, I know that 3 goes into 6 2 times. Oh, wait. 2 is a prime. So prime, 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 prime. We're done. All I have to do now is put these in order. So I'm going to start with my smallest primes. I got 3 2's, and then I have 2 3's. And we end up with exactly the same answer as when we did our factor tree. Exactly the same answer. And of course, again, you could write that with exponents if you wanted to. All right, ladies and gentlemen, we are almost done here. Next up, we are going to prime factorize 100 and the square root of 100 and compare the results. So for 100, honestly, I personally usually favor the factor tree. The factor tree just has a lot of flexibility, especially when you know this times this equals your number. And with 100, we should hopefully obviously know 10 times 10 is pretty easy. And then the beautiful thing about having double tens is if you know what times what is 10 here, then you know what times what is 10 there as well. Now be careful, ladies and gentlemen. Remember, this is factorization. You must think multiplication. Biggest error is people will write 5 and 5. But if you say 5 and 5, you're saying 5 times 5 is 10. And we know that's wrong. So it's 2 times 5 is 10. So both of these are 2's and 5's. And we know that 2's and 5's are both prime. So you know what? Instead of making individual boxes, I'm just going to make one big box down there. That'll work for me. This time, I'm going to write this with exponents because we're going to see the relationship here better if we write the exponents. So I've got two 2's, so 2 to the second power, and I have two 5's, so 5 to the second power. Now let's take a look at the square root of 100. If we have the square root of 100, well, we know we did this earlier. Square root of 100 we know is 10. So if I prime factorize a 10, well, we know that's 2 times 5. So the prime factorization of 10 is really just 2 times 5. Oh, sorry, not 2 times 10. 2 times 5. So if we compare the results here, specifically if we look at the exponents, the exponent on this 2 here is really an invisible 1. The exponent on this 5 is also an invisible 1. So ladies and gentlemen, what I hope you see here is that if you know the prime factorization of a number, its square root will have the same prime factors, but their exponents are half as big. The square root of a number will have the same prime factors. So they both have a 5 and a 2 and a 5. Will have the same prime factors, but the exponents will be half as big. And I forgot to circle my answer there. There we go. So that's a nice little shortcut, and this will come up on the homework. So when it comes up in the homework, hopefully you'll know, remember that little trick, and it can save you some work. So actually, if I know this answer here, then I don't even need that middle part. So what we're going to do here is I'm actually going to put red around that. Because if we know the prime factorization of the number, then we know the prime factorization of the square root has exponents that are just half as big. All right, finally, the last concept here, we're going to find the GCF of these two numbers using prime factorization. So, ladies and gentlemen, first things first, I'm going to copy the problem. GCF of 36 and 60, and then equals, and this is where my answer is going to go. So if we prime factorize 36 and 60, I'm going to do practice division by primes with 36 because up here we did that. We had a 36 and we missed an opportunity. We noticed that it was even, but we missed the opportunity to actually divide this by 3. Notice that this is a 3 and a 6. Well, obviously 3 goes into both of those. So 3 goes into 3 once, 3 goes into 6 twice, nice and evenly. Now if we keep factorizing, I know 3 goes into that 4 times, and then I know 2 goes into 4 2 times, and now I've got all primes. So I'm going to write this. It's going to be more helpful to do this with exponents. So starting with my smallest prime, I have 2 to the power of 2, two 2's. Next smallest prime is 3, and we have 2 of them. So 2 squared times 3 squared is 36. Now for 60, things especially that end with 0, it's really nice to use a factor tree on them. Because since this ends with 0, I know this is really just 6 times 10. Of course, 6 then is 2 times 3, which are both prime, and 10 is 2 times 5, which are also both prime. Again, put it in order. So 2 is my smallest prime, and I've got 2 of them. 3 is next, and then 5 is last. So to find the GCF here, we've prime factorized each number. Now we're going to identify what primes they have in common. So if we look at them, they both have 2 2's. They both have 2 2's. So 2 2's will be part of my GCF. Then over here, this has 2 3's, but this just has a single 3. So what do they have in common? Well, they have a single 3 in common, don't they? This guy's got an extra, but they have 1 3 in common. So times just a single 3. And then, oh, they don't have 5's in common. This guy has a 5, but this guy doesn't. So they've got 2 2's and a 3 in common. So now if we work this out, 2 to the second power means 2 times 2, which is 4. And then 4 times 3 is 12. That, ladies and gentlemen, is our GCF. The GCF of 36 and 60 is 12. And that is the end of this lesson.